Hey students, welcome back to lecture series on Z transform. For more videos, check in my I button over here, or you can check a complete playlist here in my description box. Okay, so you will get the complete playlist in my description box based on the Z transform, inverse Fourier transform, Fourier cosine sine their inverses, and a linear differential equation with a constant coefficient. Entire playlist you will get in my description box. In my today's video, I'm gonna explain to you all one of the important property for Z transform, which is a division by k. Okay. So in my last lecture, I explained to you all whenever we have multiplication for f of k, sequence f of k by some k, so we take its a derivative like minus z into d by dz of f of z, and f of z is a Fourier transform of f of k. Okay, so that one we learn in our last lecture. So in today's lecture, I'm gonna explain to you all the z transform for sequence when we have that sequence divided by some k. Okay, so when we have multiplication, we use its differentiation, and when we have division, we take its integration. Okay, so let's get dive into today's lecture. First of all, I'm gonna explain to you all the property, and then we go for some of the examples. So here I have written one important property. So whenever we have division by some k, to our f of k. Okay, so here you can see that z transform of f of k, we represent it as the f of z. Okay, that f of z we needed here. Okay, that means you have given you will be given as a f of k as a sequence. Okay, f of k as a sequence. First you have to find out its a z transform, then represent it as the f of z. Okay, and that f of z we needed here, and then we go for finding the integral. Okay, so what the property says that z transform of f of k, which is equal to f of z, then we write a z transform of f of k upon k as a z to infinity, integral over z to infinity f of z upon z dz. Okay, this one is the standard property which is important here, guys, but it's way easier. Need to understand f of z can be denominator over here, and we take its integral z to infinity. Okay, yes, so let's go for some of the example based on this property. So guys, these properties are having proof also. So if you are interested to see these proofs, let me know in my comment section. I will come up with the proofs also. But as we have little less time for our preparation, so that's why I'm explaining directly the property. In your exam, you can apply directly the property in order to get the solution. Okay, but if you want the entire proof, guys, let me know in my comment section. I will come up with the proofs. Okay, yes, let's go for finding its solution. We go for one of the example, and then we go for its solution. Okay, yes. So here I have taken one example, guys. We want the z transform of a sine of ak upon k when k greater than 0. Okay, yes, so for that finding f of k upon k, we need to apply this integral. Okay, this integral, it is the integral f of z upon z dz. So for that we need f of z over here. And what is the f of z? F of z is a z transform of f of k. Okay, and f of k, what we have here? Sine ak, because we have the form f of k upon k. Okay, f of k upon k. So what is the value for f of k here? So let me write f of k as a sine of ak. Okay, f of k as a sine ak. Okay, that means we want the z transform of sine ak. That means we want the z transform of f of k, which is a, that means z transform of sine of ak. Bracket complete. Okay, this one is the z transform we want here, and we have the condition for it k greater than 0. Okay, yes, already we learned one of the standard property, guys, for finding the z transform of a sine of alpha k. Okay, let me write that property here. Z transform of sine of alpha k, it can be greater than, okay, it can be greater than when k greater than 0. Okay, or you don't need to consider this condition. Okay, so we can write this one as z sine alpha divided by z square minus 2z cos alpha plus 1. Okay, this one is actually required property. This one actual required property that we are going to apply for sine of alpha k. Okay, yes, now let's replace as a sine ak. So we want the z transform of sine ak na. So we write z transform of sine of ak. Okay, when k greater than 0, we write what is the value for alpha? Alpha is a, we write z sine a, alpha is a z sine alpha, z sine a, guys. Okay, we have alpha as a. Okay, now see that alpha k which is equal to a k, alpha as a here. So z sine a divided by z square minus 2z cos a plus 1. This one is a z transform, okay, of z transform of a sequence alpha k. Okay, I got the z transform of a sequence alpha k, and we write a z transform of a sequence alpha k as a z or transform of f of k. We write this one as a z transform of f of k. Okay, and z transform of f of k defined as f of z. So we write this one as the f of z. Okay, this one is the f of z. So I got the value for f of z over here. This one is the entire value for f of z. Okay, so I'm going to take this f of z under this integral. Okay, and then we go for finding the integration. Okay, it is way easier, guys. Okay, let's go for substitution of this value over here. So f of z, it is needed to be substituted over here. Okay, yes. So we write z transform of f of k upon k. That means z transform sine a k upon k. We write z transform of sine of ak upon k. Okay, this one is the z transform we want when k greater than 0. Okay, so z of sine ak upon a can be written as z integral over z to infinity, integral over z to infinity, f of z upon z, f of z upon z. So what is the value for f of z? Z sine alpha, z sine alpha upon z square minus 2z cos alpha plus 1. Okay, this one is a z into sine alpha, value for z into sine alpha I written over here. Okay, z into sine alpha. Okay, so actually this is the value for f of z. Okay, z into sine alpha and z square minus 2z cos alpha plus 1. So which has a multiplicand 1 upon z also. So I'm going to write it as the 1 upon z. And out of integral we have dz. Okay, so we have to take integration with respect to dz here. Okay, yes. Now see that those are the similar term. Try to cancel, guys. Okay, so I found here this z can be cancelled with this z. With respect to dz, integration with respect to dz, sine alpha it is constant, take it outside. So sine alpha it is coming outside over here. Okay, so I will take that sine alpha outside of the integral. So we have to adjust some of the terms in order to find out some shortest form for this integral. Okay, it's not difficult, it is way easier. Okay, so take first of all sine alpha common, so we'll get the little simplified form. Okay, sine alpha outside here. Okay, under integral z to infinity. Okay, integral over z to infinity, 1 upon denominator z square minus 2z cos alpha plus 1. Okay, z square minus 2z cos alpha plus 1. Okay, this one is z square minus 2z cos alpha plus 1. Okay, multiplied by dz. Okay, this one under integral here. Now see that guys, we have to find out simplest form. Okay, because now see that denominator it is quite confusing in such a case. Okay, in such a case we are trying to operate denominator, we are trying to adjust the term here at a denominator. Okay, so that we can find out alternative part for integration. Okay, now we can see that it is a z square minus 2z cos alpha plus 1 it is there. Okay, so can we add or can we subtract some of the terms? So we can write a square minus b square, a square plus b square, or some another term that we can apply under integral, like a dx upon integration of dx upon x square plus a square, or a square plus x square, such a form. Okay, yes. So let me add some terms here, let me subtract some of the terms here. Okay, so that we can write some standard form for this sequence. Okay, so let me adjust the denominator. I'm trying to adjust the denominator over here. Okay, so I'm taking that denominator separately. z square minus 2z cos alpha plus 1. Okay, I taken that denominator over here. I'm going to adjust some of the term over here. Yes, now see that a square minus 2 times a b, okay, plus b square it is remaining. Okay, so we can apply a term like a square minus 2ab plus b square. Okay, such a expansion. Okay, so a square means we have z square. Okay, minus 2 times ab means minus 2 times what is the value for a, z. Okay, a value for a, z, and value for b, it is a cos alpha. Okay, plus b square we want now, that means we have a which is equal to z and b which is equal to here cos alpha. Okay, a which is equal to z and b which is equal to cos alpha, so b square will become cos square alpha. Okay, so we add here plus cos square alpha minus cos square alpha plus cos square alpha minus cos square alpha. So you can cancel this one, you left here in the original term. Okay, yes, and we know that z square minus 2z cos alpha, okay, z square minus 2z cos alpha plus cos square alpha can be written as a minus b bracket square. Okay, so we can see that a square minus twice of ab plus b square, it is the expansion for a minus b bracket square. Okay, this one is the expansion for a minus bracket square, like say that a square minus 2 times a into b plus b square, we write a square minus b a minus b bracket square, that means z minus z a minus b, that means z minus cos alpha bracket square. Okay, now see that this entire term and this term, so I written in this form. Okay, yes, and next what we write plus left term 1 minus cos square alpha, 1 minus cos square alpha. Okay, 1 minus cos square alpha. So we know that 1 minus cos square alpha is the sin square alpha, as we know that sin square alpha plus cos square alpha which is equal to 1. Okay, so 1 minus cos square alpha which is equal to sin square alpha. Okay, take that cos square to the other side, we get the sin square alpha. So we write z minus cos alpha bracket square plus sin square alpha. Okay, yes, so I solved this denominator, like this way. Okay, so this one is actually expansion for z square minus 2z cos alpha plus 1 as z minus cos alpha bracket square plus sin square alpha. Okay, yes, so we go for substitution of this value over here, and so we write sin alpha as it is outside. Okay, under bracket integral over z to infinity 1 upon z minus cos alpha. Okay, z minus cos alpha bracket square plus sin square alpha. Okay, which is out of dz over here. Okay, yes, I written this way. It's a way easier for solving, guys. Okay, yes, it is not difficult. So we go for applying some standard formula for finding the finding its differentiation. Yes, so I taken cos alpha, but instead of a cos alpha, what we have here, cos a. We have cos a, guys. Okay, not only cos alpha, it is a cos a. And instead of sin alpha, we have sin a also. Okay, so I taken alpha as it is here, as it is the formula, but it is actually the value for a. So this one is a, this one is a, this one a, this one a, this one a, this one it is also a, this one also a, this one a, this one it is also a, this one it is also a, this one a, and this one a. Okay, yes, so I'm going to add one standard formula for integration that we all are familiar with this one. Okay, so let me write this standard formula. Okay, so we know that integration over, okay, 1 upon x square plus a square. Okay, x square plus a square dx can be written as 1 upon a tan inverse of x by a. Okay, so this one is our required integration formula. Okay, 1 upon x square plus a square, 1 upon a tan inverse x by a. Now see that dx with respect to x as x square, and remaining another term which is not another than x variable, we consider it is a. Okay, yes, now see that dz with respect to z, this can be become as x term. Okay, with respect to dz, z become x, and as sine alpha or sine A, it is completely constant with respect to dz. Okay, yes. So but I will get the values over here. Let me write this value here. So I can write x as here. So compare this one, dz with respect to z minus cos alpha. Okay, x is a z minus cos alpha. X, I got the z minus cos alpha. Okay, and a, what is the value for a? Sine alpha. Okay, sine alpha. But in actual, in the form of our sine of ak, so we have a. Okay, that means we have x as a z minus cos a, which is in our example given. Okay, and a as a sine a. Okay, so replace these two values in our integral so that we will get the simplified form of the integral, and at the end substitute the limit z to infinity. Okay, yes. So I'm going to replace these values over here. These two values I'm solving. Okay, that means 1 upon x square plus a square. Okay, that means 1 upon a. So we write next step 1 upon a. 1 upon a means 1 upon sine a. Okay, 1 upon a means 1 upon sine a. Okay, this one is the expansion of this integral, guys, only. Okay, I'm solving this integral only. Okay, yes, this integral I'm solving. After getting the answer, I'm going to put the values over here. Okay, yes, 1 upon a tan inverse of x by a, that means z minus cos alpha, upon sine, cos alpha means cos a. Okay, z minus cos a upon sine a. Okay, bracket complete. 1 upon a tan inverse x by a. Okay, yes, and which is having limit, which is having limit. What is the limit? Integral over z to infinity, and multiplied by sine alpha is there. Okay, so write a sine of a, it is there. Okay, bracket complete. This one is the required term. Okay, now see that as we have integral with respect to dz, so we are going to replace z as a infinity and z here. Okay, so sine a, it is completely constant with respect to dz, so we can directly cancel this one. Okay, sine a can be cancelled directly, so we left here with the term tan inverse of z minus cos a upon sine of a. Okay, bracket complete, and integral over z to infinity. Okay, this one is our required limit. Okay, for our integral. Now need to replace the infinity z to infinity value, you will get the required answer. Okay, not a difficult, need to remember one or two forms. Okay, yes. So put the value first. So if I'm going to put infinity first, okay, z as infinity, so infinity minus cos alpha upon sin alpha, that means entire term goes to infinity. That means infinity minus something, infinity plus something, infinity multiplied by something, infinity divided by something, it always infinity. Okay, that means we write a tan inverse of infinity. Okay, tan inverse of infinity. And what is the tan inverse of infinity? We write a pi by 2. Okay, because pi by 2 and 3 pi by 2 or 2n plus 1 pi by 2 gives the tan inverse as a value infinity. Okay, yes, so we write tan inverse of infinity pi by 2 minus, replace z as a z, so it is a term remains same, tan inverse of z as a z means it remains z only, cos a upon sin a, bracket complete. Okay, yes, this is the actually z transform of sine of ak divided by k, z transform of sine ak divided by k, which is equal to pi by 2 minus tan inverse of z minus cos a upon sine a. Okay, yes, so you can keep this one as it is, or you want simplest form. We know that pi by 2 minus tan inverse, pi by 2 minus tan inverse of theta can be written as cot inverse of theta. Okay, so you can take this one also. Okay, pi by 2 minus tan inverse of theta can be written as a cot inverse of theta also. Okay, so you can apply this pi by 2 minus tan inverse of theta as a cot inverse of theta. So we write a cot inverse of z minus cos a, z minus cos a upon sin a. this one is our required Z transform of sine of AK upon K. Okay, guys, it's not difficult, it is way easier. Okay, I hope you all have understood my entire lecture. Okay, if you want to note this notes, write these notes down. Okay, so you can take this one from here. Okay, so this one is the standard property I considered here first. Z transform V of K divided by K can be written as integral over Z to infinity of Z upon Z dz. Okay, yes, and next I took one of the example. Okay, so if you want, you can take these notes as for your reference. Okay, note it down. Okay, this one is the entire notes. Pause the video, check out these notes. Okay, so this one is the entire notes for my today's class. I hope you all have understood, guys, here in my today's lecture. Nothing is difficult. Okay, so even after, if you found anything difficult, guys, let me know. To make just one single video, guys, it's really time taking and effort you. Okay, it will need lots and lots of effort. So I hope you can understand my efforts. Okay, so if you found anything useful, guys, let me know in my comment section. Or if you have any doubt, difficulty, or if you want to solve some difficult question, or if you have any challenging question, guys, let me know in my comment section. I'm not only solving the questions from Z transform, I'm solving the questions from another subjects also, like real analysis, complex analysis, all the pure mathematical subject, ordinary then applied mathematical subject like ordinary partial, and many more subjects. Okay, you are always welcome to put me your doubts on my comment section. I will be loving to solve these questions. So that is here for our today's lecture. So thank you everyone, thank you for my today's lecture.